Hi everyone, I'm going to present this paper, the Hawk's edge partition model for continuous time event-based temporal networks. My name is Sikun. This is joint work with Heinz Koeppl. So in this paper, we are in particular interested in modeling temporal interaction events, where each event has a time step and involves two participating nodes. The one is sender and the other one is receiver. Sometimes we may also have a content sent from one node toward another. So in previous study, we always discarded the time step information to obtain a single network snapshot aggregated from this temporal interaction events data. From this single network, we can infer the latent community structure and perform the link prediction. Alternatively, we can also discretize this continuous time events data into the regularized time interval to form a discrete time dynamic network from which we can infer the evolution of the underlying latent community structure and perform the temporal link prediction for each snapshots at different time points. However, discarding or discretizing the time steps may lose a lot of information for us to infer the underlying causal relationships among the individuals, and that can lead to the poor predicting of future events. However, in this paper, so our goal is to model the continuous time dynamic networks. So in particular, we are interested in modeling the underlying latent community structure behind this temporal interaction events data straightforwardly and learn how this latent community structure influences the reciprocating interaction dynamics among the nodes. So for example, as shown in this figure, so we have a single network snapshot aggregated from this continuous time events data. So we factorize the adjacency matrix corresponding to this single network snapshot to infer the underlying community structure. And given the estimated latent community structure, so we partition the temporal interaction events data into the different clusters. And for each cluster, we learn the reciprocating dynamics behind the clustered events data independently. So more specifically, in this paper, we propose the Hawk's edge partition model, which consists of two components. So one is to modeling the latent community structure, and the other one is to try to capture how the latent community structure influence the reciprocating kernel, reciprocating dynamics between the different cluster events. So specifically, to model the latent community structure, we resort to a recently advanced network community detection method, the edge partition model. So given the single network snapshot as shown in this figure, so the edge partition model represents each node with a positive feature vector. Each element of this vector captures how strongly that node is affiliated with the different latent communities. So in short words, the edge partition model can be considered as an overlapping community detection method. And the number of latent communities is automatically determined by this method in a non-parametric based manner. So for temporal interaction events, so reciprocity is a very common social phenomenon. So it means one person's action towards another increases the probability of the same type of action being returned shortly afterwards. So for instance, in the illustration example, if Bob sends an email to Helen, Helen is more likely to send an email back to Bob in the near future. To capture such reciprocating behavior, so we model the interaction dynamics between each pair of two nodes using the mutually exciting Hawk's process. As shown in this figure, so if Bob sends Aaron an email, the intensity that Helen sends an email back to Bob will increase by an increment which exponentially decay over time. So the intensity function for the pairwise mutually exciting Hawkes process is shown in this equation. So the main idea of the Hawkes expectation model is, so we have a single network snapshot aggregated from the temporal integer one's data, as shown in this figure. So we factorize the corresponding adjacency matrix to infer the underlying latent community structure in particular. So we assume each event between the two nodes is driven by the latent communities behind these two nodes. As shown in the figure, the first event from V to U is due to both U and V are fitted with the first latent community. So accordingly, this event can only influence the intensity from U to V of the same type. Therefore, we naturally induce a clustering structure over the observed events. The reciprocating dynamics is updated accordingly for each cluster independently. So to demonstrate the proposed method, we conducted experiments on real-world data for the task of temporal link prediction. In short words, the task of the temporal link prediction is we have the events from 0 to t as the training data to infer the model parameters for all the different methods. Thereafter, we use the trained model to predict there being a link from t to t plus pi hat. We evaluated all the methods using the RC curve and the precision recall. So we compare to the two state-of-the-art methods, the dual latent space Hawkes process model and Hawkes stochastic block model. They are highly related to our model. So applied to the three real-world data across the different settings by varying the training ratio. So the proposed model, the Hawkes expectation model, achieves a higher accuracy compared to these baselines. So finally, I want to quickly give a conclusion about our model. The proposed Hawkes expectation model can capture how the underlying community structure influence the reciprocating dynamics among the node between the different latent community pairs. So using the data augmentation strategy, the model inference is done using the expectation-maximization algorithm and the Gibbs algorithm for the maximum posterior. So we evaluated the model performance in temporal link prediction compared to the several state-of-the-art methods and prove the performance gain of our proposed model.